I'm sorry, everyone. Let's start off. Last class, we have finished with ray optics. Now, in ray optics, like I said, there are two more parts. One is your optical instruments and one is dispersion. Both are there only for main, so we will do them later on. Just a bunch of lot of formulas again. Another, I think, both of them combined, you'll get another 10, 12 formulas. So we'll see that stuff at the end. Today, we'll be starting off with magnetic force and MEEC. Again, this thing also has three parts. One is the magnetic force, then magnetic field, and then bar magnets. Again, bar magnets is mostly mains portion, so that also we'll do later on. So we will primarily handle the force and the field part right now. Sure, no other scams on. Great. So what is this magnetic force? So this thing, right, again, it starts from an experiment. Normally, if you see, right, everything that we have seen, entire science is about that. You see an observation and you try to make laws out of it to explain the whole thing. So magnetic force is also one such thing. So consider we have a charged particle. So this is where people started noticing something of this sort. When you keep charged particles or when you put current wires together, they started noticing there's a force between them. Consider a charged particle in presence of a wire. So let's say case one. You have a current carrying wire I, and then you took a charge there and you kept it near the wire. Plus Q at rest. And what do we observe? Like I said, again, it's an experiment. The observation is nothing happens. The charge does not move. Now, so far in whatever we studied, right, we know only actually two types of forces. One was a gravitational force and one was electric force. So this thing implies that that means there is no electric field. Because if the electric field had been there, the charge would have moved. Meaning there was a small doubt. Maybe if the current flows in a wire, maybe it is producing electric field, but it doesn't produce, and it kind of makes sense because think about it. When you say charge is flowing through the wire, it doesn't mean there is a net charge. A wire is still neutral. For every proton here, there is one electron, isn't it? The electrons are simply jumping from one place to another. So the wire is still neutral. It is not a charged wire or something. It is a neutral current wire. So it kind of makes sense. There is no electric field as expected. Right? Since there's no electric force. This was the first thing. You kept a charge near a current wire and nothing happened. I said, okay, makes sense. Fair enough. Then, second case, you took the same wire, you took the charge Q, but this time you gave velocity V. You gave some speed to it. And if we observe, this thing starts actually deviating. This thing starts bending towards the wire. This is the observation that you notice in the experiment. We see charge deflects. That is, velocity changes. That means there is a force. This is surprising because just now we established a fact. There's no electric field. Tell me one thing. Does electric field act only when you're moving? Electric field does not care about your velocity, right? It depends only on the charge. So case one established the fact there is no electric field. And now suddenly out of nowhere, you're saying there is a force. And that to look at this weird force. This force is coming only when you have velocity. We have never dealt with a force like this, isn't it? Gravitational force, G m1 m2 by r square. Electrostatic force, k q1 q2 by r square. If you look at all these forces, it never depended on velocity of the particles. Gravitational force dependent on the masses, electrostatic force dependent on the charges. But this thing is something weird. So there is a force, and one thing is clear: this is not electric force. Because if this had been electric force, you would have moved in case one also. So this is where people started thinking that means we are dealing with something new. That is how you actually do anything in science. If you see stuff and you observe, and then you start making names out of it. So one thing is clear: this is a new kind of force. Which depends on the charge and the velocity. And people noticed something similar happening when you keep near magnets. So somewhere down the line, the name came out to be this force is called magnetic force. And the field is called magnetic field. Because if there is a force, there will be always a field. Generally, for these kind of things. Remember what is the field theory? So field is like a system will generate field lines. So that is how the two things communicate with each other. So it's like that spider thing which I told you. So here the field responsible is called magnetic field. Now, you need to understand something. In science, we always study the how ka part. Meaning, if I know, think about this. If I throw a particle from a building, I know where it will land. I know in how much time it will land. I know with what speed it will land. I know at what angle it will land. I can literally find everything that you want about the particle. But I can't answer one simple question. Why is the particle getting attracted towards Earth in the first place? Then you will say because of the mass. Then I'll ask you why mass is creating gravity, and we don't have an answer at some point. So the thing is, we know how gravity works, but we don't know why it is there in the first place. You're getting it? That is how the entire science is. If you think about it, everything fundamentally, right? The moment you know how it works, but the moment you ask why, you have no clue. That is a fact. Getting it? And we just keep trying to create more theories to explain that, but at some point you have to stop and say, I don't know. So magnetic field is also something of that sort. We know it is there, but we don't know why it is coming, right? It's just a fundamental thing in the nature. So case one, case two are clear. Now case three. So then people started theorizing this stuff. They realized there is something weird. And later on, we will see actually, when people thought there was only electric field and started doing things, they started getting wrong results in some experiments. So plus q, same story. I'll give the velocity v here, and I know this thing deflects. Now let's bring two observers. Let's say we have an observer A at rest. We have another observer B here. So B is going with speed v initially. Parallel to this thing. Now, if you ask person A, boss, what do you see? A will say, okay, this is case two because I'm at rest. I think the charge is moving. This is case two. And the reason why this charge is bending is because of magnetic field. We just explained all that. He will say magnetic force is acting. Problem came when you ask the same question to B. Because B ka velocity is constant. So isn't he in an inertial frame? So he's in an inertial frame. So when you ask B, B will say, initially my relative velocity is zero. initially. At least the starting point may be relative is zero. So I think the charged particle is at rest. So technically, this is case one. So there should be no magnetic force. But I still see this particle is bending. And people are clueless, like what the hell is happening now? Like in this frame, why are you not able to explain? You can't even use pseudo force or anything. There should be no magnetic force. Right. So, and the only other force we know which will act on charges is the electric field. So again, let's not get too deep into this. This thing, you can actually explain this using relativity, but I will not go there. This is actually electric field. This must be due to electric field. Because there is no other, force which will act on a charge, isn't it? There are only two forces, either an electric force or a magnetic force. If you're saying this is not magnetic force, then you don't have an option. This must be electric field. This must be due to electric field. And then when people started working on this more and more, right, people realized actually electric field and magnetic field, right, are two sides of the same coin. That's why we call them electromagnetic fields. You don't separate them out. So initially people thought electric field was different, magnetic field was different. Later on we will see, we'll have a relation also. We have something like dou E by dou X is equal to minus dou Y by, dou B by dou T, something of this sort. You'll have relations between them. Like I said, we'll not get into that part. But the main theme is this. Electric fields and magnetic fields are not independent quantities that dependent on each other. Depending on the frame of reference, you can see sometimes only magnetic field, sometimes you can see only electric field, sometimes you can see both. So whenever you're studying anything related to electromagnetism, you should include E and B, electric field and magnetic field, together and study. If you study only electric fields or only magnetic fields, certain cases you will start, your equations won't be valid anymore. They'll start going wrong. Like in this case, there is no way to explain what is happening in beaker frame. So that's it. We will just say that statement and we will end it up. More on this, we don't have at our level, so we'll not get into it. Electric and magnetic fields are dependent on each other. Depending on the frame of reference. Maximum, if that I'll ask you something on this, it'll be theoretical question. They'll give this question only. They'll say there are two observers. They'll ask you which force is A seeing, magnetic force, which force B is seeing, electric force. They can't ask you anything more than that. And like I said, it is out of our scope to do anything more on this. So people thought like that. And later on, when they kept on studying, right, they realized it is not only electric and magnetic field, even quantum mechanics gets combined with this. They call it QED, quantum electrodynamics. So people combined electric field, magnetic field, they combined quantum mechanics with it. Great. The only thing that we are left now is gravitation. We are unable to combine gravitation with quantum electrodynamics. And that is where these people are working on a theory called a string theory, the theory of everything. There is one theory which can explain every force that is there in the nature. People have been working from last 40 years, but still. We can see either magnetic or electric or both. If you have another person who is going at some weird angle, he can see both. Clear with this? So, like that, we established the fact there is something called a magnetic force, and that is how we start the whole thing. Clear with this? I know there are a lot of question marks like what and all, but like I said, if you ask sir why a current wire is getting magnetic field, we have no clue. If you can explain that, you'll get a Nobel Prize. So it's like asking why gravity is there. The only reason you didn't ask in gravity is because you see it every day, right? You think it is normal. If I drop a particle, it will fall down. So it was obvious to you. You never bothered to ask why. But the moment I ask you the question, if I drop something, why does it fall? You will say Earth will attract. I say, why will Earth attract? Because of gravity. Okay, why gravity comes? Because there is a mass. Okay, why mass creates gravity? I don't know. You stop. At some point, I keep asking why. You will stop at some point. So, magnetic field looks weird because we have don't encounter this day to day, so it looks weird, but gravitation is as weird as this. Gravitation is actually even more weirder than this, actually. Here, at least you can go up to a few levels. You can say when electrons move, they create something and all. Gravity, there is just mass and done. There is nothing there fundamentally. So people are actually trying to search for a particle called graviton. Just like electrons, which can explain charge, people are trying to find particles called gravitons. There's also a particle called Higgs boson, which can explain mass. That was a god particle, they call it. So story goes on. So if you're into particle physics, you will encounter all that stuff. Thinking, why is it? Next thing. So magnetic force. We have some 6, 7 cases. We will see the first 4 cases today. Magnetic field. The symbol is B bar. So this is generated by current carrying wires, magnets, moving charges. So even when a charge moves, it behaves like a current. So that current produces magnetic field. We ignored this thing in electrostatics. If you remember, the first definition of electrostatics was this only. We study slow moving charges, neglecting any magnetic effects. And time varying electric fields. This was the thing. If you have an electric field which is changing with time, that actually produces magnetic field. And the best part, you are in an electromagnetic field at any point of time. You're in a light is an electromagnetic wave. Right now, you're talking to me, the phone signals are electromagnetic signals. So you're actually being flooded with electromagnetic signals at this point of time. You have a Wi-Fi in your house, you're bathing in electromagnetic signals. 2.4 gigahertz, the Wi-Fi. If you're doing a 5G, so it is a 5 gigahertz ka Wi-Fi. So there are 2 signals passing on. Your Wi-Fi, your bottom floor ka Wi-Fi, upper floor ka Wi-Fi, Airtel signal, Jio signal, Vodafone signal, literally. Your body is being bombarded by signals from every point. So let's see the 4 cases. Case 1, like I said, again, all these are experiments, observations. From there, we figured it out. You take a magnetic field and you keep the charge at rest. You take a charge particle, plus Q, keep it at rest in presence of a magnetic field. Symbol is B bar. What do we observe? We observe nothing happens, charge remains at rest. So this case 1 tells you this magnetic force depends on the velocity also. This is actually the biggest clue. It is not electric field. Okay. Case 2, the velocity vector is parallel to the magnetic field. Means you take the charge particle Q and you project with velocity V. In presence of a magnetic field, B is also parallel. We will notice this guy just keeps going straight without any deflection. There is no change in speed, there is no change in direction. That means velocity is 0. So this gives you a clue. That means this thing not only depends on velocity, it is also depending on angle between V bar and V bar. We observe no change in velocity. That is magnetic force is 0. And you can clearly see, if you look at sine theta, cos theta between these two, when you theta is 0, sine theta becomes 0. We don't take tan theta because tan anti goes to infinity. You can't have infinite force. Generally, you can kind of approximately guess. So this must be depending on sine theta also. Clear with these 2 cases? The case 3 is the one which will give you the major hint, how it looks exactly. Any doubts on this page? Case 3, When you take the velocity perpendicular to b bar, you see something really weird. You have a magnetic field B and you take up charged particle Q, and when you project with V, this thing starts going in a circle. We have never seen a force like this which will make you go in a circle. Now, before going into this, so when you say cross, cross means into the plane. We have seen this in vectors long back. Minus k cap. Dot is in out of the plane, which is plus k cap. So we observe here, this thing starts going in a circle with constant speed. Uniform circular motion. And we know if you're going in a circle, there should be someone to provide the required centripetal acceleration. And I can't think of any other force here other than the magnetic force. There's only one possibility. So here, the magnetic force is providing the required centripetal acceleration. And it is always perpendicular to the velocity. Why? Speed is not changing now. If the magnetic force is at an angle, then the speed would have increased or decreased. Since the speed is remaining constant, then there's only one possibility. The force must have been perpendicular. So magnetic force is providing the centripetal acceleration. Again, this is all the things you're getting from the observation. You see an observation and you're trying to pick out data from there. And perpendicular to velocity. Since the speed is constant. Now, when you combine all these data points, and again, a few more experiments, you come up with something. They came up with the magnetic force is given by charge, velocity, b, and the angle between them, sine theta. Again, like I said, you do few things and get all the data there. And when you combine all this vectorially, this turns out to be q v cross b bar. It's a vector cross product. Here, theta is the angle between v bar and b bar. There, this is our first formula. Completely derived from experiments. So technically, this is the only formula. From this formula, we get everything. Now, the most important thing here is getting the direction of this force. So it's a cross product. Let's see how to do that. We know how to find A cross B ka direction from vectors. Right? Next thing. Now let's see the direction of the force. So listen to this carefully. This is important. If you mess up the directions, the whole thing will go for a toss. I'll show you two ways. You see whichever you like and you use it. The first thing, we will just use your regular A cross B. So place your palm. We'll use a right hand thumb rule. Place your right hand ka palm along V bar and curl your fingers towards B bar. Try to make a fist. Right? The thumb then gives you the direction of the B cross B. Now, example, let's say if you have velocity V this way, and let's say we have a magnetic field into the plane, right? So see how to do this thing. So look into my screen. Huh? So let's say velocity is forward, right? Velocity is pointing face forward. Magnetic field is downward. Are you getting the direction? See, north, east, west, south, up, down. 6 directions in your room. Let's say velocity is in front of you, V bar. V bar is down. So put your hand on V bar. I can keep it two ways, right? I can keep it horizontally or I can keep it like this. There are two ways I can keep. You're getting it? Velocity is forward. I can keep it like this, or I can keep the palm facing the ceiling. B is which way? B is down, right? B is down. Now, can I make a fist like this? I can't make a fist. So put the other way around. Now make a fist. So your palm should go towards B. So when you make a fingers like this, thumb is pointing which way? Your left hand side, isn't it? Your thumb is pointing your left hand side. Can you see the direction? So the V cross B direction would be that way. This would be the direction of your magnetic force. This is still little easy. Like, see, what is V bar ka direction? V j cap. What is B bar ka direction? B minus k cap. What is j cross minus k? Minus I cap, na? Remember vector cross product? I can do like that also, but every time you won't be so lucky to get exactly x and y. They can be at angles also. We will see more. I'll show you more examples. So the picture would be, this is the thing which I was talking about. So this would be the force. If this is the velocity and if this is your B bar, you're getting how is the rotation? Your finger should go from V towards B. Then the thumb will indicate the force ka direction. Let me give one more example. Let's say, what if you have V this way and B this way? Now, your V is on the right hand side, right? So you can put you can put your hand like this or like this. There are two directions every time. You can put the palm facing up or palm facing down, right? Yeah, in this case. So you want to go towards B, right? B is which way? B is front. So put your palm on V and turn towards B. So you should slap B basically. V is going and slapping B. Think of like that. So V and will go towards B. The thumb will point which way? Up. So here the force will be, force is up. So this is nothing, like it is just your screw basically. If you think about it, see, if I see this bottle, I have a big one. Look at this thing. If I want the bottle cap to come out, what should I do? Look at your right hand thumb rule. If you want the bottle cap to come out, look at the direction here. It is like this. Meaning if I rotate the cap like this, the cap comes out. If I want the cap to go inside, means my thumb should be down, means my rotation should be this way. If I rotate like this, the cap becomes tight. You can try with your bottle cap, you will see it becomes tight. Basically, it's your right hand screw. So did you ever get confused sometimes, when you're opening a screw, should I rotate that way or this way? Sometimes you rotate in that direction, it becomes tight. So this is, you use your right hand thumb rule. If you want the screw to come out, so thumb should be out. That means you should rotate in this direction. The finger should curl this way. So basically the thumb gives you the direction of the motion and the fingers will give you the direction of the screw car rotation. So here you're rotating from V towards B bar. Is this making sense, everyone? So here V rotates towards B. Then the thumb will give you the direction. Is that clear, everyone? This is one way to do, okay? Now there is another way. In case you're not comfortable with this, you can take your seat. Look at the three fingers. Take the three fingers, the thumb, the second finger, and the third finger. The middle finger, thumb is your first finger. Second finger is your, I don't know what they call this. What they call this? They call something, whatever you want to call. The index finger. That's not the index. Index only, na? Index. So the index, the middle one, and the thumb. So we have three like a gun, okay? Now look at the directions here. Your index finger will be velocity. This will be velocity. The middle finger will be magnetic field. The thumb will be the force, like a gun. Again, if you think about it, it is the same thing. See, if this is velocity, if you look into my screen, if this is velocity, this is magnetic field. When V rotates towards B, thumb is pointing up, na? Same thing actually. You're getting it? If you rotate V towards B, if the rotation is this way, thumb is pointing up. It is the same thing. So this is a more simpler way. You can put the thing like a gun here. So if you put this in the direction of V, if you put this in the direction of B, the thumb automatically shows the F car direction. Now look at the first example again. Velocity is which way? Front. So put the index finger front. Magnetic field is which way? Down. So put your middle finger down. Open your thumb. Thumb is pointing left. Make sense? Look at the second case. Velocity is which way? Right. So put your index finger right. Magnetic field is which way? Pointing in front of you. Put your finger like this. The middle finger is facing in front of you. The thumb is pointing up. Are you able to get this direction? Your index finger is pointing right. You show it to the right. Right. Your middle finger is pointing to the front. Open this in the front. Open your thumb. It points up. Are you sure with the directions? Both are kind of actually the same thing. You see whichever is convenient to you. So it's like this. So if you have a hand, put your hand like this. I'm putting a devil's hand. Your fingers will be like this. So you need to rotate your hand inside. When you rotate it inside, the thumb will point that way. Or you can use this gun ka thing, whichever you like. The three fingers thing. Both are kind of same. We'll do four more examples. So here, this is what you can do, the three directions. The index finger or the second finger, right, is towards V bar. The middle finger is along B bar. If you keep these two in that direction, then the in thumb will give you the direction of the V cross B. So I'll give you a few examples. So you try this and tell me what will be this. If you got this, I think the force cut action is clear. Let's say velocity is this way. Magnetic field is this way. Charge is plus Q. Velocity is this way, B is this way. Let's say this is minus Q. Let's say this is V and this is B. This is plus Q. B is inside. B is this way. And luckily, right, here they need not be always perpendicular also. You can just rotate V towards B using that. You need not be exactly perpendicular. Minus Q. There, let's get these five. I think if you got this, you will get the hang of it. Try for a minute, then I'll show all of them. Then you can see whether you got it right or not. Be careful. Force is QV cross B. So thumb only gives you V cross B. Huh? If the charge is negative, you should take opposite of it. So it will feel like you're making all weird signals with your hands. I still remember when you're writing an exam on magnetic force, the invigilator thought we all are copying and sending signals to everyone. That guy made a mess out of it. He caught all of us and he went to the principal to complain. He said, like, bloody, it is a magnetic car test. How are you supposed to find directions? So people were doing like this, like this, like this, like this, and all. So that guy thought we are copying and we are sending answers to everyone. So not his fault. Teacher was laughing. So done. Should I show you? Finish for another 30 seconds, then I'll show you. You can verify whether you got them right. Then in case you didn't get it confused, you can ask me if you didn't understand. Using your right hand or left hand, record? You have to use your right hand. Use your right hand. This is called right hand thumb rule. Let's see the first one. V cross B. I don't know which one you're using. Anything is fine. So if I try to use the three fingers ka thing, V is pointing left, B is pointing up. So thumb will point this way. This will be the force ka direction. Got this? Or you can put your hand on V and rotate towards B. B is up, so I'll rotate up. So this will point forward. There's a third way also, like I said, you can choose this thing will be like what, minus I cap, and that is K cap. So minus I cross K plus J. That is also fine, but this rotation method, right, works even when the angles are not 90 degrees. What about this thing? V cross B. So be careful here. This is V cross B ka direction. But since the charge is negative, force will be this way. Sure, everyone. So put your finger towards northeast. Put your finger towards northeast. See, front is north, right is east, west, south. So in the second example, the finger is towards northeast. The magnetic field is down. So put your middle finger down. The thumb will point northwest. Yes. The thumb will point northwest. But the force charge is negative that way. You want to use rotation? What to do? Take your palm. Look at this thing. Take your palm. Put your palm in the direction of north, east. B is which way? B is down, na? So I need to rotate down. You have to slap B basically. So thumb will point northwest. But since it's a negative charge, it will be opposite to that. Are you guys able to visualize this? Put your hand horizontally, like a paper. Don't do like this in the screen. Put it horizontally on a paper. That will be more easy for you to realize. Don't put it on a screen and you'll get confused. Imagine it's on a paper. So front is north, south, east, west, up, down. Are you clear with this? What about the third example? See, here V is pointing up, so finger will be up. B is pointing southwest, so it will be like this, isn't it? V is pointing up, the middle finger is pointing southwest, thumb will point southeast towards Australia. Make sense? And since it's a positive charge, force also will be that way. Anyone confused with so far? Please ask. Look at this example. Velocity is southwest, that is towards Africa, right? Magnetic field is towards Singapore, right? So again, rotation would be easy here. Velocity is this way. So V is rotating towards B. Now look at this. V is rotating towards B. V cross B. You can use your hand actually. V cross B. Thumb is pointing up. So thumb will point up. So V cross B is up. But remember, it is a negative charge. So force is down. Thumb only gives you V cross B. What about this guy? Here, V is pointing down. So thumb is down, right? And your middle finger is this way. The thing is pointing north. Sometimes it becomes difficult to twist your fingers. So this thing, if you can visualize it like this thing, see, V is down, B is this way. So V goes towards B. So V should rotate this way. Are you able to see the rotation? V rotates towards B. So this rotation is what? So V is rotating this way. So you can see the rotation there, how it goes. It's like this. So it is pointing up. Clear? Sometimes you get confused, then just go back to I cap, J cap, K cap. V bar is minus K cap. B bar is minus I cap. What is K cross I cap? J cap. Done. So if you feel sometimes confused, you can use that. So there are three ways you can do it, however you want. You will get comfortable, but get used to this. Any doubts on these 5 examples? All sure? The direction part is important. Next thing. So we established the thing, it is going in a circle. So the magnetic field is B, velocity is V, velocity is V, velocity is V. You can clearly see here what is the force cut direction? The force cut direction is up toward the center. So at every instant, the force is towards the center. It is always perpendicular. And this force is being balanced, right? It's balanced, giving the centrifugal force mv square by r. This is a case where V is perpendicular to B. So this magnetic force is providing the required centripetal acceleration mv square by r. And here the force will be qvb sine theta, but theta is 90 is equal to mv square by r. So we end up with r is equal to mv by qb. This is your second formula, everyone. And the time period is 2 pi r by velocity, circumference by speed. If you substitute r ka value, you'll get 2 pi m by qb. And here, since force is always perpendicular to velocity, the work done by magnetic force is always zero. So magnetic force will only change the direction. It will never increase your speed because the force is perpendicular to V. There, these are your second formulas, everyone. Radius and the time period. Clear with this? There, we started with QV cross B, and we said this is, since you're going in a circle, that should be equal to centrifugal force mv square by r. From there, we got the radius and the time period. Any doubts on this? Clear with this? Now I can't actually show you charges going in a circle, but we can do something similar. So here, the blue thing which you're seeing, right, is actually a cathode ray beam. You can see that small blue line. The blue line, what you're seeing is actually an electrons being ejected out and the gas is getting ionized. So what you're seeing is not electrons, but the gas which is getting ionized. Whenever the electrons pass through the gas, they're ionizing it and you can see the blue light. So at the bottom, you can see two numbers there, 250 and 0.00. 250 is the voltage. That means these electrons are being accelerated by a voltage of 250 and they're being pushed out. And the 0.00 is the magnetic field. So just now we saw, what is the radius ka formula? mv by qb. So if the magnetic field increases, the radius becomes smaller. So initially there is no magnetic field. So radius is infinity. That means it's a straight line, almost a straight line. Now see what happens if you put a magnetic field. Can you see how the beam is bending? So we have a magnetic field of 0.98. That's almost 1 Tesla, I guess. You can see 1.2 weight, it's bending. There you see a circle. So these electrons which are being ejected, they start going in a circle like this. So that R which we got is the radius of this circle, mv by qb. Now, look at the bottom. The numbers are increasing. Look at the radius of the circle. The radius becomes smaller, 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 smaller. So this is at maximum 3 Tesla. We get a very small circle. So this is how you can visualize particles going in a circle. So what you're seeing is an ionized gas. If you decrease the magnetic field, again circle becomes bigger, 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 and then it becomes a big curve. Able to see that? This is a small setup. Like if you put a very high voltage between 2 points, remember we get that arc, electric arc. So now you put a magnet close to by, you can see how that thing is bending. So those are actually the stream of charged particles which are moving, and you put a magnet close by, they start bending and deviating. You can find an electron beam at one more place. Do you guys remember this old Onida TVs? Dabba CRT monitors? Must be seeing in some labs also. The monitor looks big. Nowadays they're kind of outdated, but when I was in school, this is a TV in everyone's house. We used to have that big thing. We call them CRT monitors. CRT is a cathode ray one. So the concept is at the back of this thing, there is a cathode ray machine. It sends electrons. When these electrons hit this part of the screen gets ionized, and you can see colors and all that stuff. So that is the concept of the TV there. Nowadays we use LCDs and LEDs and all, so different thing. Now that means in this TV there are electrons which are coming from the back and hitting. So if you put a magnet in front of it, you can deviate the electrons. I did this and spoiled my TV like this. So you take a magnet. Now when you get that magnet close to the TV, can you see how the screen is bending? That's because the electrons behind which are coming, they're deviating. So if you can put really close, you can see black hole. The electrons are deviating so much, they're not hitting the screen there, so screen looks blank. So one day I found a magnet, I was playing, and when I kept it near the TV, it started doing this. I thought it was fun. I played for some 10-20 minutes. After that, the screen colors became permanent. Right side became yellow, left side became red. The TV had become pretty weird. It became like this. I didn't tell my mom, I just kept my mouth shut. My mom thought the TV got spoiled on its own. I told her when I got into IIT though. Almost after a decade. There, this is how it looks when you bring it. One of the best places you can find electrons, a CRT monitor. They produce a lot of heat and they take up a lot of electricity. So we don't use them nowadays. And they don't give enough colors also. There. So you can see the Dabba monitor there, piche. That's actually a big cathode ray tube. The electrons are coming there and you're deviating it. You can see how the entire screen is messed up. So there, that's how it looks. So you do see charges moving and all, but you can see only in terms of phenomena. So you don't see literally charge going. Clear with this? There, that is the best I can prove it to you. Actually, what I'm saying is not some my imagination. It actually happens. So let's see a question. We have an alpha particle and a proton. A proton is 1h1, a hydrogen nucleus, and an alpha particle, which is a helium nucleus, 4He2 plus, are projected into a magnetic field. Find ratio of their radius and the time period. When, case 1, they're projected inside with same velocity. So you take an proton and an alpha particle and throw them into a magnetic field with same speed. Find the radius, find the time period. They're thrown with same momentum. They're thrown with same kinetic energy. They're thrown with same potential difference. Matlab, you accelerate both of them with the same potential difference and then you send into the magnetic field. Same electric field for same time. You accelerate both the particles with an electric field E for same time and then you send it inside. same electric field for same distance. So let's say you have an electric field E, make them travel for a distance D, and then you send into the magnetic field. 6 cases, everyone. They'll ask you any one. And similar question I'll ask you again in modern physics. Find the ratio of de Broglie wavelength. So we can play with the same thing later on. So how do we do this? So let me show you what I'm asking. Listen to the first one. You said same speed. So what is the radius curve formula? R is equal to mv by qb. So here speed is same and b is also same. So R is proportional to m by q. So radius of proton by radius of alpha particle is mass of proton by charge of proton, mass of alpha by charge of alpha. I'll take mass of proton 1, charge 1, then alpha ka mass will be 2 and charge will be 4. Mass will be 4 and charge will be 2. So this will be 1:2 ratio. Understood what I'm asking? Time period is 2 pi m by qb. If you notice something here, this is independent of velocity. It is always m by q. So this is also Tp by T alpha is also half. And luckily, this is same for all the cases. For all the 6 cases, the time period is same. It only depends on mass and q. It doesn't depend on velocity. So it doesn't matter what you do. So there is no need to find time period for all the cases. Got what I'm asking now? Now can do the remaining 5 cases for the radius. Time though will be same. So that is done. Get the ratio of radius for the rest. I'll give it 2-3 minutes, then I'll show you. Show you the second one. Second one, you said same momentum. So R is equal to mv. So m into v is same. So R is proportional to 1 by q. So Rp by R alpha will be 1 by proton ka charge is 1 and alpha ka charge is 1 by 2. 2:1. Got that? Get the third one. Time period will be always half only, right? So there is no need to find time period anymore. So T is always m by q only. What about same kinetic energy, same potential difference? Same kinetic energy is a pretty good mains level question. Right, Puroja. Right, Rehan. Which one, Aditya? Ahana, which one is that? Which case you guys are typing? You have to tell me that also. I won't know. Near Aditya, that is wrong. Near Niharika, that is wrong. Right, Saish. What about the case C? So what is kinetic energy? Kinetic energy is half mv square. Multiply and divide by mass. This will become mv whole square by 2m. This becomes momentum square by 2m. We did this in mechanics. Therefore, momentum is nothing but root over 2 into mass into kinetic energy. That means your radius ka formula becomes mv, which is momentum by qb, is root over 2 times mass into kinetic energy by qb. So kinetic energy is constant. So R is proportional to root m by q. Are you getting the proportionality? So you need to create kinetic energy in that term. So replace momentum with root 2m kinetic energy. So radius of proton by radius of alpha will be root 1 by 1 for the proton, and this is root 4 by 2. 1:1. Got that, everyone? That's how you do for the kinetic energy. What about D? If you accelerate them by same potential difference and then you leave them inside, then what is the thing? Try. I think you got reverse. Rp by R alpha I want. And we use the formula to get ratio of velocities and then replace. Yeah, you can do that. But even then you still get 1:1, right? Maybe you must have messed up the calculations. There's nothing wrong with that, but a little longer, but answers should come. Mass is 1:4 ratio. So velocities will be, I think, 1:2 ratio. 2:1. So look at the fourth one. What is kinetic energy? Kinetic energy of a charged particle is nothing but charge into potential difference, isn't it? If you take a particle across a potential difference V, it will gain energy Q into V. That means you can make this formula root over 2 times mass into kinetic energy by QB. You can convert this into root over 2 into M into charge into potential difference. I'll just put a big V there. QB. So this is proportional to root over M by Q. So you can replace kinetic energy with charge into potential difference. So we get Rp by R alpha will be root over 1 by 1 by root over 4 by 2. 1 by root 2. And interestingly, if you look at case 6, same electric field for same distance, we know VA minus VB is nothing but minus integral E dot dr. That means the potential difference delta V is nothing but E into distance. That means if you have same electric field for same distance, you'll have same potential difference. So if E and D are same, then delta V is also same. That means this is as good as case 6. So D and F ka answers are same. So this is case 6. So D and F are the same thing. Clear with that? So electric field into distance will give you potential difference. So indirectly you said the potential difference is same. What about case E? Same electric field for same time. Try. That's also a good one. Another 30-40 seconds. That's it. Your whole job is somehow in that formula MV by QB, you need to introduce these terms. If you said same electric field for same time, you have to get E and T in the formula. What is force? dP by dt. So change in momentum will be force into time. Change in momentum is m into v, initially you're at rest. Force is E into Q into T. Therefore, radius is equal to mv by qb. This will be E into Q into T by qb. This is Et by B. Interestingly, if you see this is constant. Electric field is constant, time is same, B is same. So independent of the particle, as long as it is charged, the ratio is 1:1. Means you take a helium nucleus, you take a sodium nucleus, you take anything, it doesn't matter. All will have 1:1 ratio for this case. Clear with this? Getting the proportionality is important because this itself will be a question. R is proportional to what? Root m by q, m into q, m square q. So that itself will be a question. All clear with this? So same thing I can ask you in de Broglie wavelength. What is de Broglie wavelength? H by mv, na? Now I can play with this mv here. mv is root 2 m kinetic energy and all that stuff. So I can ask you all the 6 questions for the de Broglie wavelength. Next one, let's say we have magnetic field here. B. We have a charged particle here, Q here, M here, going with V. So this thing enters inside and does something. Can you draw the trajectory and the time spent inside the magnetic field? On the right hand side, there is a field. On the left, there is no field. Draw the trajectory and the time spent inside the magnetic field. Get this is an easy one. B is 0 on the left hand side, right? I'll not write only better. How is the force, Ravihan? Did you get the direction? Force is towards north. V is which way? V is towards right. See, I'll tell you a simple thing. V is towards your right. Just put your hand to the right. B is which way? Down. So rotate your hand down. No. So what is the direction? So this is the direction, right? Put your hand V here. Rotate it down. Na. Thumb is pointing front. Put your hand on V and rotate towards B. Slap B basically. That's the meaning of it. So what is this thing here? So once it enters here, remember this is the velocity V. Magnetic field is down. So force will be which way? Up. Did everyone get the force? Force is pointing up. So force is perpendicular in the interface. That means, see, one thing I know, it will go in a circle. So that means center is somewhere here. This particle will take this as a center, will go in a circle like this, and then it will come out again with V and goes off in a straight line. Technically, it wants to complete a circle, but by the time it comes out, there is no field, so it will just go out in a straight line. This will be the center here. This will be your radius, where radius is equal to mv by qb. Since you're doing only half of the circle, the time period will be t by 2, which is pi m by qb. Is that easy? Sure. Can you tell me how will this guy look like? Suppose if you have magnetic field on both the sides, let's say this beta value is B here. This is also this way. Let's say this is 3B, 3 times the magnetic field. Now, if you launch a particle from here, plus Q, mass M, and with V, can you draw the trajectory? How will this path look like? This is one chapter where you can get really weird paths. Did you get it? So this thing enters inside here. This is the velocity. This is the force. So center will be somewhere here. So this will make a semicircle like this. It will come out. It will enter here. What will be the force ka direction now? V is this way. Force will be down, na? But this time the radius will be smaller. This will be mv by qb. This is q times 3b. Here the radius is r is equal to mv by qb. Means you'll get only 1/3 of the radius. So you will get a smaller circle. Then it will come out again. It will go till here. Then again it will go in a big circle. Again it will come out here. Again it will go in a smaller circle. Then again it will go in a bigger circle. You're getting? This will never stop. This radius will be r by 3. Is this thing clear, everyone? This will keep on repeating. It'll just keep going up. First it will go 2r. So what is this total distance? This total distance will be 2r. So every time it will go 2r up, and every time it will come down by 2r by 3. Is this clear? I can ask you find the time period of this motion actually, kind of something like that. All clear with this? Take a small break, come back by 9:42. Any doubt so far? Right. Chalo, come back in 5 minutes. Let's say you're sending a particle plus q, mass m with speed v. This is angle theta. Same thing, you're sending a particle angle theta, but this time charge is minus q, mass m v. Now can you draw the paths and the time spent inside? Now be careful here. Here velocity is still perpendicular to b bar. V bar is in xy plane, and b bar, v velocity is in xy plane, and b bar is minus k cap. So theta is the angle between velocity and the interface. So don't think theta is the angle between v and b bar. There. Let's get the draw the paths and the time spent inside. One thing is clear: you enter a uniform magnetic field, you'll go in a circle. So find the direction of the force. So that will give you the center. So for this guy, where is the center? So velocity is this. So V cross B, if you see, force will be this way. Meaning center is somewhere here. So using this as a center, and if you try to draw a circle, V is going this way, it comes out like this, isn't it? And you can clearly see here, if this is theta, this is 90. This will be 90 minus theta. This will be 90 minus theta. That means this is 2 theta. So this will be a circular arc of angle 2 theta. Therefore, the time will be unitary method. For 2 pi, you get time t. For 2 theta, you'll get 2 theta by 2 pi into capital T. Capital T is 2 pi m by cubic. What about the green one? The green one, if you see, again, be careful. V cross B will be this way. But since it is a negative charge, force will be opposite to that. Meaning center will be here. So using this as a center, this will go in a bigger circle like this. This is how the path will be. Just now we proved this is 2 theta. That means this will be 2 pi minus 2 theta. Therefore, for this time will be 2 pi minus 2 theta by 2 pi into capital T. Are the paths clear, everyone? One is a small arc and one is a big arc. The negative one will go in a bigger circle. Have a look at the shapes. Same thing. Find the direction of the force. The center should lie somewhere on that line, which will be at a distance r. So the radius of both the circles is mv by qb. There. Taking the center and the particle, draw a circle, and you're done. Got this? Devansh? Clear? Sit straight. Next one. This is a good one. Let's say we have a wall, E is equal to 1, perfectly elastic collision. This is the top view you're seeing from the top. You have a particle here, plus q, mass m, projected with speed u. Now, this particle is at a distance of r by 2. There r is your regular radius, mb by qb. Means what? Technically speaking, this would go on in a circle like this, isn't it? But before completing the circle, you'll hit the wall. There's a magnetic field B here, neglect any gravity. Draw the trajectory. So how will the path look like? And find the time interval between two collisions. So this will not just stop one, this will just keep hitting the wall. Draw the trajectory. And time interval between two consecutive collisions. Two d by 3. That is right. See what's happening. One of a geometry. So this guy starts from here, it goes and hits this thing. So initially the force will be like this. So center is somewhere here. So from here to here, if you join this, remember this will be tangential here. This is r by 2 and this is radius r. So this angle is 30 degrees. So this angle is 60 degrees and this angle is also 30 degrees. Clear with that? That means you're going to hit the wall at an angle of 30 degrees with the normal. So now when you try to draw the path, and we know it's a perfectly elastic collision, oblique collision it is. So whenever you hit at an angle 30, you'll bounce with what angle? 30 on the other side. If that is 30, now again, V cross B, if you see the force ka direction will be something like this. This will be your center. The force will be like this. So using that as a center, if you draw a circle, it goes like this. and hits the wall again. Again it hits at 30 degrees, again bounces with 30. Again it will go like this, hit here. Again it will go like this, hit here. You're getting it? This will never stop. It will just keep on hitting and going. Able to visualize this. It just keep moving to the right, just keeps on colliding forever. Now, if you just look at this circle here, so from the center, we saw this angle vertical. This is 30 degrees. This is 60 degrees. 60 degrees and 30 degrees, meaning this is 120 degrees. Meaning it is going in a circle of 240 degrees. Therefore, the time will be 2/3 of the time period. Is that clear, everyone? It's more of a geometry. You're not letting it make it a complete circle. All clear with this? Can someone tell me what happens if E is 0? Instead of E is equal to 1, if E is 0, then can you tell me how will the path look? I'll give you a minute. If E is 0, how will this look like? Will it stop? Let me ask you this again. We did this discussion few times. Suppose if you have a ball here coming with speed v and hits the floor and E is 0, what will happen? It will just come and stop. The component along the perpendicular will become 0, but it will slide with the horizontal velocity, right? So even in this scenario, something similar will happen. So if you take E0, you're coming here and hitting at an angle of 30 degrees. So if you look at the components here, this will be u cos 30 and this will be u sin 30. So u cos 30 will become 0, but u sin 30 will remain. And if u sin 30 is there, remember there is still a magnetic field. So if you go with u sin 30, that is u by 2, and in this magnetic field, you will go in a circle. So this is how your path will look. You will start somewhere here. You will go like this, hit, and then you'll go in a circle. You'll just keep going in a circle forever. And this circle radius will be r by 2. Make sense? This becomes 0. Sure with this? What if E is not 0, but E is half or something? Then how do you think approximately it will look? Approximately. If E is equal to half, approximately how do you think it will look? So every time you hit, what will happen? The component will become E power V cos 30, E square V cos 30, E cube V cos 30, isn't it? The horizontal will remain same. That means this guy, when it hits here, it will make a big one. The next it will make a small one. Then it will make even a smaller one. And eventually, this will not become 0. Eventually, as you keep going, it will reach this state again. You will reach r by 2 ka state. Because that u sin 30 will never become 0. Making sense? You will reach the E is equal to 0 case. That is how it would look. Clear with this? So there, you can actually have a Rangoli competition. You can use this stuff. Put a magnetic field, put a charge, and just leave it, and whatever paths you get, just start drawing them. Next thing. Let's say we have a charge q, mass m, projected with speed u, but this time you have a magnetic field which is changing with time. B naught is constant. So this guy will not go in a circle. You have a time varying magnetic field. So this will take some weird path like this. Delta is your deviation. Find delta at time t. If there's a time varying magnetic field, there'll be an electric field. We neglect any induced electric fields. Anyway, we don't know how to calculate them right now, so we'll not worry also. But just in case I'm mentioning it. Technically, there'll also be an electric field here that will mess up the speed. So we're not going to get into that. Find delta at time t. This is a kind of a question which is, you have to think a little, but it looks scary, but it is easy to solve. B is increasing with time. Conservation of angular momentum and energy. I know. I told you if it doesn't have any path or something you can use. But tell me one thing. What is work done by magnetic force? Zero. So there is nothing called energy. Velocity is constant. तो क्या करोगे उसके साथ? And there is a magnetic force. It is not pointing towards any particular point. It is changing direction. So think. Take a minute. How will you think? When I saw this question for the first time, you know what I saw? I thought, okay, B is there, B not T, all are there. Okay, this thing looks scary with time and all. But then said, what are you asking in the first place? You're asking for an angle at time T. Then I started thinking in physics, all of physics, where did I see theta and time together? So it is circular motion. And this question looks like I have to do some integration, isn't it? That means I need theta as function of time t. So where do we get a theta t in terms of time? Isn't that omega angular velocity d theta by dt? Meaning, at least that is what I thought. Okay, omega is there. I said, but how the hell do I get omega from here? I said, okay, what is omega? V by r. Do I know V? Yes. Do I know R? Yes. Now, if you think about all those things, they actually come together. Try. I told you how to do it. That is your thought process. That is how you think. You don't see the question B not T and get scared. You see what is being asked. Then you start thinking, okay, where did you see something like this, or where are these things coming from? And then see if you can connect this to something else. So clicks. You do this some hundreds of times, and then your brain will think this is normal. And that's what we're doing in this 2 years. I think that's what we did last 1.5 years. And that's what we'll do for the next whatever time is left. And you have seen something like this before. You have done more deadly version than this. Using this problem as a reference, I made up one problem long back. I don't even remember. Right, Om? So here, if you see, this thing is actually going. So initially, this was the circle. Then this was the circle. As you're going, the radius is becoming smaller and smaller. So your angular velocity is v by r. Speed does not change because work done by magnetic field is 0. Radius is mv by qb, not into t. Omega is d theta by dt. V actually cancels off. So qb naught by mt. So we get d theta is equal to qb naught by mt dt. Integrate on both sides. 0 to delta, 0 to t. Q naught by mt square by 2. Easy? You know where you have seen this before? Anyone remembers? Anyone remembers this problem? Variable mass system. The rocket ka thrusters are perpendicular to the rocket, and the rocket starts deviating. Find the angle of deviation as function of time t. याद आया कुछ? This problem I made up using this magnetic field का question. I got inspired and I made this up. Theta is the deviation for every small time रे पूरा. In small time dt deviated little, मतलब देखो यहाँ पे in small time dt you deviated small angle d theta. In the next circle you deviated d theta. You're adding all those deviations. And if you see, we did something similar here. This was actually more messed up because mass was changing with time. You got a log function. This was a much tougher one than that. Should definitely go through this question. This is the last question in center of mass collisions. Clear with this? Next one. Let's say this time we have a patch of magnetic field. So we have a particle here which is entering at an angle alpha and it is leaving at an angle beta. The distance length of this patch is d. Particle ka charge is q, mass is m, and enters with speed v. Find the relation between alpha and beta. A particle q and mass enters a magnetic field region. So only the magnetic field is for distance d. At alpha and leaves at beta. Find relation between alpha and beta. That will be the first question. Find the average force acting on the particle. So during this time interval, when it is inside, what is the average force? In the region. Let's see how we do this. If I put alpha 0, that's a standard mains level question. This is much better. Others, keep your cams on. How do we approach? Like I said, this is mostly a geometrical stuff. All these things we see in is all geometry. Isn't this a part of a circle? So it starts from there. That's a part of a circle. And if you look at the force directions here, so the force will be something like this initially, perpendicular. So center should lie somewhere on this line. Similarly, this is also perpendicular. So somewhere on this line. So center will be outside here. And the radius of this circle will be mv by qb, the standard one. So from here, if you drop a perpendicular, if this is alpha, this is 90 minus alpha, this guy will be alpha. Similarly, if that is beta, this is 90 minus beta, this whole angle is beta. Let this distance be x and let the distance be d. So if you take sine alpha, that will be opposite side, which is x by r. If you take sine beta, we are talking about this triangle, everyone, sine beta. That would be d plus x by r. You're done, subtract them. You get sine beta minus sine alpha. Where does red line go? Sine alpha is d by r. There, that's your general result. Just be careful, beta must be less than equal to 90 degrees. What is beta greater than 90? Meaning this surface is so thick, it entered inside, made a circle and came out. Na? We don't want that case to happen. So beta must be less than 90 degrees. Clear with this? And if you make if alpha is 0, this, like I said, this is your standard case. This is actually easy to solve. Means you're entering like this. Then you'll go out like this. So in this case, it is pretty clear. The center is somewhere here. So you'll get sine beta is equal to d by r. Want to find omega, integrate, do all that. What are you trying to integrate actually? Integrate v cos theta from beta to alpha and equate to td. God, what are you even integrating? This at every instant, this angle is changing.
Yes, so we are integrating the cos theta along with, means that cos theta we can use omega. So we'll integrate along with the changing part of that angle.
Try karo. हो सकता है. You can try. But
Try
why to
saying
do
that.
so much? It was easy. You can find omega integrate v cos theta from beta to alpha, but why will you integrate omega to beta to cos alpha? What is the time ka limits?
So we're taking
Omega is d theta by dt. You're integrating with what? There's a time there. How did you get d in that? Clear with this? The question is still not over, but you can make this something even better. What if you don't have a single region, but you have multiple regions? And not only this, these multiple regions have magnetic field messed up. Like one is up, one is down, one is up, one is down, and so on. And let's say the distances are also different. D1, D2, D3, and so on. So here, now when you enter at an angle theta, you'll go like this. Because the magnetic field direction is reversed, you will turn like this. Then again, you'll go like this. You're getting how it will go? Every time the field reverses, the radius of curvature will reverse, and eventually it will come out from here at an angle alpha n. Again, remember alpha n is less than 90 degrees. So again, we can use the same formula. So the final angle for the first surface will become the initial angle for the next surface. So if you try to apply the formula here, for the first one, you will get sine alpha 1. So this angle will be alpha 1, and here it is entering with alpha 1 here, and this will be like alpha 2 here, and so on. Sorry, this is alpha 2, and this will be alpha 3, and so on. This will be sine alpha 1 minus sine theta. It will be d1 by r1. Sine alpha 2 minus, wait, actually, this is also theta only. This is theta. This is alpha 1. This is alpha 2, and so on. I didn't draw the picture up to scale. So this will be sine alpha 1. This will be minus. Because the radius of curvature is reversed, you put a minus. So on, if you do this till sine alpha n, you get a telescopic function. And when you add all of them, they will cancel out here. So you get a neat result. So you'll get sine alpha n minus sine theta will be summation here. So it will be d1 by r1 minus d2 by r2. If all the fields are in the same direction, put a plus sign. D3 by R3 and so on. Yeah, it has nothing to do with refractive index. Don't mix up stuff. Refractive index क्या था? Mu into sin theta constant था. So here what is the deviation? Deviation is again alpha n minus theta. There. If you have n mediums, you can play like this. Clear? You can do something even better. What if the field is having a variable magnetic field? Let's say something like B is equal to B naught x. The magnetic field is changing its position. Same story, what we do, but this time we'll take a thin region. So this thin region can be treated like a small region, just like what we did, whose thickness is dx. So if you look at our formula that we derived, which was sine alpha, so sine theta final minus sine theta initial was nothing but summation sigma di by ri. So if I want to integrate this for small angles, then this will become sine theta final minus sine theta initial. Sigma is replaced by integration, isn't it? And d becomes dx, that is the thickness of the small region, and r is the radius in the small region. This will become dx, r is nothing but mv by qb, where b is changing at every instant, b not x. There, this is your general formula in case if you have a variable magnetic field region. And if you try to solve this with what we got, sine theta final minus sine theta initial, this will be qb naught by mv, limits will be x dx. This will go from 0 to d. qb naught d square by 2mb. There. Are you clear with this? So this is a case when you have a variable magnetic field. If you have a field changing with x, can you see how we made this problem? We started with what? At an angle. This is still a good problem at a mains level. Huh? If you make alpha 0, that will become a CET level question. If you have multiple regions, this is also good advanced question. I can make it even better. Can you see how we took that one question and we see how many levels you can have? You can just keep making it tougher and tougher. Any doubts on this? Clear with this? There is still one part of the question, average force. वो कैसे निकालेंगे? What is average force? F average is nothing but change in momentum by time. Delta P, don't take dP. That is mv final minus mv initial by time. Now, one thing here, luckily, the speed never changes. So when you're leaving here, you're going V with an angle beta. When you're entering here, V at an angle alpha. So if you look at this angle here, this will be your delta, which is your deviation. Delta is nothing but beta minus alpha. This was alpha, this was beta. So this angle will be delta. That means if you look at these two vectors, we have one velocity vector v, another velocity vector is same speed v, and the angle between them is delta. Remember, this is your v initial vector and this is your v final vector. If you join them, you will get delta v bar, isn't it? That's an isosceles triangle. So delta v, that's from triangle of vectors. Delta v is v final minus v initial. We get delta v is equal to 2v sine delta by 2. That need not be. So if you join them here, this will be delta v. It's an isosceles triangle. Both the sides are equal. That's your delta v. So f average would be 2 m into delta v by time. How do you get time? That angle is delta, right? This entire arc which you got, this angle is delta. So the time taken will be r delta by speed v, arc length by arc length by speed. That is the time you have to use, Vihan. So time will be the arc length, which is r delta by speed v. There, you got everything. So this will be 2 mv sine delta by 2 by r delta by v. That's your average force everywhere. Clear with that? This fifth question, I can ask you a lot of stuff like this. You can make it really better. Any doubts on this? This is the B part. Clear? Next thing. Case 4. What if V bar is at an angle to B bar? X, Y, Z. Or let me just show you first normally. So let's say we have velocity V like this and B bar horizontally at an angle theta. So how do we deal this? We split the velocity into components. So split the velocity into two components. We have V sine theta, B. We have V cos theta and B. Now, if you actually think about it, doesn't this look like case 3? V sine theta and B are perpendicular. Doesn't this look like case 2? Both are parallel. Now, if both the things are perpendicular, then what will happen? You will go in a circle. The radius of the circle will be mb, but here v ka place mein you have v sine theta. And if you go in a straight line, then you will go with a constant speed v cos theta. If you combine a circle and a straight line, what do you get? A helix. Is that making sense? Split the velocity into two parts, v sine theta and the v cos theta. V sine theta will make you go in a circle. V cos theta will make you go in a straight line. If you combine both together, isn't that what we do in principle of superposition? You'll get a helix. So if you send v at an angle, you get a helix. This is what I'm saying. This is one chapter which will go in any weird paths you can create. And this distance between the two threads is called one pitch. So when you look at a screw, the distance between the two threadings is a pitch. So pitch is nothing but the horizontal distance traveled by the particle in one time period. which is nothing but u cos theta into time. And what is the time? Interestingly, your time actually doesn't care about anything. It is always 2 pi m by qb. It has no velocity part in it. So is this is case 4, a helix. Clear with this? There, you combined case 2 plus case 3, you created a helix. So it's not nothing, technically it is not new. Next one. So let's see a question on this. So x, y, z. The magnetic field is in the x-axis, so it is b I cap. The velocity v bar, this is theta. So let's say this is v cos theta I cap, v sin theta j cap. So velocity is in xy plane. Particle is projected in xy plane. And the magnetic field is along x-axis. Find the coordinates of the particle at time t, starting from origin. So if you leave this particle, I know it will go in some weird path. Find the coordinates of this particle at time t. If you can find coordinates, actually you can find everything for this. From origin. Let's get this. Try. I'll give 2-3 minutes. Let's see how will you think about this. First of all, figure out how this is traveling. See, make it into two parts. V cos theta, V sin theta. V cos theta will make you go in a straight line. So just ignore that guy. Let's talk about V sin theta. Start from there. Imagine you have only V sin theta. Study that first. Let's finish off. Last one for the day. See, that must have given some energy. So if you actually talk about the V sine theta, P here, this is your V sine theta. How is the force cut direction? You can clearly see here, that is J cross I cap, so it's minus K cap. The force is towards this side. Got it? Meaning this will go in a circle, something of this sort. This will be the center. So the circle will be in XY plane, YZ plane. So circle is in YZ plane. Now, if I just rotate this whole picture by 90 degrees, this is Y, this is Z, and X is coming out. This is your negative Z axis. This circle, right, is actually looking like this. Are you able to visualize this? That is how the circle is going. The circle is going in YZ plane where the center will be 0, 0, minus R, where R is MV sine theta by QB. Is that circle clear, everyone? And this particle, how it is going? This particle is going like this. So after time t, it will reach somewhere here. This angle will be alpha. So this particle is going in a circle like this in YZ plane. Because with what speed? With V sine theta. So here we'll get alpha will be omega t, and omega is nothing but V by R. So that will be V sine theta by R into time. Or you can use 2 pi by capital T. That is also fine. So the angular velocity will be 2 pi by capital T, and alpha will be omega t. Time period is 2 pi m by QB. That's your angle there. Now, just to show you in a big circle there. Remember, this was your origin 0, 0, 0. This was your negative Z axis. This point ka center is 0, 0, minus R. After time t, it is somewhere here. This is alpha. This will be R sine alpha. This will be R cos alpha, but we're not interested in this. We're interested in this, R minus R cos alpha. Agreed? So here, and if you drop a perpendicular here, this distance here is R minus R cos alpha. This distance here is your R sine alpha, which is your Y coordinate actually. Therefore, if you see, your Y coordinate will be R sine alpha. Your Z coordinate will be minus R into 1 minus cos alpha. Your X coordinate is cool. This guy is simply going with V cos theta. That guy doesn't care about anything. This is your Vx. So your X coordinate will be V cos theta into T. Be careful, there are two angles, theta and alpha. Theta is the initial angle between V and B. Alpha is that angle in that circle. Don't mix up both of them. Right? So now if you combine these two and you're done, that's your coordinates. If they ask you for the position vector, it will be R bar is equal to V cos theta T I cap plus R sine alpha J cap minus R into 1 minus cos alpha K cap. Check. Clear with this? Can you tell me again at what point will it cross the x-axis? This is not a proper circle, right? It's actually helix. So if you actually look at the path, so this guy is going like this. It will again graze somewhere here, na? You're getting it? So it will be, meaning if you look at the side view, your helix, you can see how it is grazing. It will keep touching these points, isn't it? Basically, that is your pitch, isn't it? That is your pitch, which is nothing but v cos theta into time for one revolution, which is v cos theta into 2 pi m by qb. There. So these points will be origin. This will be p comma 0. This will be 2p comma 0 and so on. It will keep touching x-axis at every p. Able to visualize the path? You know this thing, how it looks? If you ever been to this fair or something, you must have seen this thing in stalls. They take that stick, they put the potato here and they open it. Kaya wo potato wala? Then they put it in that masala and all, and then they fry it and give it to you. I don't know what they call it, some potato swirl or something. You guys never ate it? It is fine. It's tasty though. Okay, that's a bit about it. That's up to case 4. So next class when we catch up, we will do case 5 and 6. And then we'll go ahead with something called magnetic force on a wire. But we will be just playing with that one equation QB cross B. Everything comes from there. Okay, with that, we'll wrap up for the day. And I think the deadline was still today. I hope everyone has given it. I'll be posting the results and the new paper tomorrow. There is still time though. Someone has to give it to there till 11:30. So okay, with that, we'll wrap up for the day. So any doubts in the class note? Anything else you can ask me, or else you're free to leave. I'll see you guys again Monday, same time. So take care, stay safe.